Look at the darkness between stars on a clear night. Every shadow you have ever seen is simply light blocked. But the darkness at the center of a black hole is different. Light does not pass through it, around it, or escape from it. It ends there. Space itself bends so severely that the geometry of the universe breaks, and at the center waits for something that our best mathematics cannot describe. Tonight, we will descend through every layer of a black hole, from the visible boundary where light ceases to escape, down through the warped architecture of space-time itself, to the place at the center where all known physics dissolves, and arrive at the extraordinary questions that physicists are still fighting over today. Before we dive in, if you love exploring the deepest mysteries of the cosmos as much as we do, take a second to like the video or subscribe, and tell me where you're listening from and what time it is. Now, let's begin. There is a story we tell about black holes, and it goes something like this. A massive star burns for millions of years. At some point, gravity wins. The star collapses. What remains is an object so dense that not even light can escape. Simple, dramatic, satisfying. That story is true, in the same way that saying, "a wave is water moving," is true. It captures something real while leaving out almost everything that actually matters. What lies inside a black hole is not a simple question of density. It is not, as a popular description so often implies, a matter of extraordinary weight compressed into a small volume. The interior of a black hole is a place where the ordinary architecture of reality, the rules that govern how things move, how time flows, how information persists, has been replaced with something that our two greatest theories of physics cannot agree on. General relativity, the framework Einstein gave us for understanding gravity and spacetime, describes the interior of a black hole with mathematical precision, right up until the moment it doesn't. Quantum mechanics, the framework that governs everything at the atomic and subatomic scale, offers its own set of demands about what must be true inside a black hole. And those demands contradict the first framework in ways so fundamental that resolving the contradiction may require rewriting the laws of physics entirely. This is not a problem that belongs to the far future of science. It is a problem that sits at the center of theoretical physics right now, generating arguments between some of the most brilliant minds alive, producing proposals so strange they stretch language almost past its breaking point. The black hole information paradox is an unsolved problem in physics, a paradox that appears when the predictions of quantum mechanics and general relativity are combined. It has been generating breakthroughs and contradictions for half a century, and it remains unresolved today. But before we can go deep, we need to understand what a black hole actually is. Not the popular version, the real version. And the real version begins somewhere surprisingly specific, with a soldier sitting in a trench during the First World War. In the winter of 1915 and 1916, a German physicist and astronomer named Karl Schwarzschild was serving on the Eastern Front. Albert Einstein had just published his general theory of relativity, and the equations he had written down were considered so complex that most physicists assumed no exact solutions would ever be found. Schwarzschild, sheltering from artillery fire somewhere along the Russian front, found one. He wrote it down and mailed it to Einstein. It was the first exact solution to Einstein's field equations, and described the geometry of space-time around a perfectly spherical, non-rotating mass. What Schwarzschild found, embedded in his own solution, was something that made physicists deeply uncomfortable for decades. A surface at a specific distance from the center, now called the Schwarzschild radius, where the equations seemed to suggest something had gone catastrophically wrong. At this surface, the component of the metric tensor describing time went to zero, and the component describing radial distance went to infinity. The mathematics appeared to break. For a long time, physicists interpreted this as a sign that real objects could never actually collapse to such densities. The Schwarzschild radius was considered a mathematical artifact, a singularity that would never be physically realized. Einstein himself wrote a paper in 1939 arguing that real matter could never compress far enough to fall within its own Schwarzschild radius. He was convinced the object was physically impossible. Then the theorists looked more carefully at the mathematics. What Schwarzschild had found at his critical radius was not an actual physical breakdown. It was what mathematicians call a coordinate singularity, an artifact of the particular coordinate system he was using, rather than a genuine infinity in the underlying geometry. You can encounter the same kind of thing on an ordinary map of the Earth. The geographic North Pole appears to have a mathematical problem in standard longitude-latitude coordinates, but the pole itself is perfectly ordinary ground. In 1958, the physicist David Finkelstein showed that Schwarzschild's troublesome surface was indeed a coordinate artifact. The surface itself was real. It was the event horizon, the boundary of no return. But there was nothing physically violent about it. An observer falling through it would feel nothing unusual at the moment of crossing. This was the first great revelation about black holes, and it deserves to be dwelled upon because the implications are still not fully absorbed by popular understanding. Everyone knows that a black hole is a region from which nothing escapes. The textbook picture is of a place with such extreme gravity that even light cannot climb out. That picture is essentially correct. But here is what almost nobody tells you when they present that image. Crossing the event horizon, the boundary itself, would feel like nothing at all. There would be no wall, no explosion, no sensation of transition. Space-time at the event horizon of a large enough black hole is perfectly smooth and locally indistinguishable from any other region of space. The event horizon is not a physical object. It is a location in space-time, defined not by what is there, but by what cannot happen there. Nothing can escape from inside it. But crossing from outside to inside involves no local drama whatsoever. This is one of the most counterintuitive truths about black holes, and it has enormous consequences. It means that an astronaut falling into a sufficiently large black hole, the supermassive black holes that sit at the centers of galaxies, for instance, would cross the event horizon without any immediate physical signal that the crossing had occurred. They would not feel a sudden acceleration. They would not encounter a wall of fire. They would look around and see for a moment a universe that appeared relatively normal. The difference would announce itself only later as the inward pull of gravity strengthened and the destination became unavoidable. To put a number on the scale involved, the Milky Way's supermassive black hole, Sagittarius A star, located roughly 27,000 light-years away from Earth, is more than 1,000 times smaller and less massive than the black hole at the center of galaxy M87. The Event Horizon Telescope's observations of Sagittarius A star revealed a bright, thick ring morphology with a diameter of about 52 microarc seconds, consistent with the expected appearance of a black hole with a mass of approximately 4 million times the mass of the Sun. For a black hole of that mass, the Schwarzschild radius, the radius of the event horizon, is roughly 12 million kilometers. That is an event horizon larger than the Sun. An astronaut falling toward it would encounter tidal forces so gentle at the horizon that they would be imperceptible to any instrument the astronaut carried. For the black hole at the center of M87, the the supermassive giant that became the first black hole ever directly imaged in 2019, the mass is approximately 6.5 billion solar masses, and the event horizon is so large that our entire solar system could fit comfortably inside it several times over. Crossing such a horizon would feel like nothing. Stay with that for a moment, because it quietly overturns something fundamental. If you could somehow be present at the crossing of a black hole's event horizon, you would not know you had crossed it. The laws of physics in your local vicinity would be identical to what they are anywhere else. The event horizon is invisible, undetectable by local instruments, physically unremarkable. Its defining characteristic is not anything you can feel or see. It is a causal boundary, a one-way membrane in the structure of space-time that separates regions of the universe that can communicate with the wider cosmos from regions that cannot. This quiet, unremarkable nature of the event horizon is itself at the heart of one of the deepest crises in modern physics. We will arrive there in time. For now, though, there is a more immediate question to address. Before we can discuss what might be inside a black hole, we need to understand how black holes form, because the interior structure depends in ways that matter enormously on the story of how the black hole came to exist. The most common pathway begins with a massive star. Not every star becomes a black hole. In fact, most stars do not. Our own sun will eventually exhaust its nuclear fuel and collapse into a white dwarf, a dense, hot remnant roughly the size of the Earth, supported against further collapse by the quantum mechanical resistance of electrons being pushed into the same states. Stars somewhat more massive than the Sun will end as neutron stars, objects a mere 20 or so kilometers across, supported by the quantum mechanical resistance of neutrons against compression. But there is a limit to how much a neutron star can resist, and beyond roughly 2 to 3 solar masses, even neutron degeneracy pressure cannot hold. Gravity wins completely. Relatively light stars retire as white dwarfs, in which nuclear burning has ended, and inward gravitational pressure is stopped by a degenerate electron gas. In 1931, Subrahmanyan Chandrasekhar discovered that this works only for masses up to about 1.4 solar masses. Heavier stars collapse into neutron stars, typically after a supernova explosion. But these also have an upper bound on their mass, the current value being about 2.3 solar masses. Stars more massive than this cannot stop their gravitational collapse. When a stellar core collapses beyond the point where neutron degeneracy pressure can intervene, the implosion is extraordinarily rapid. The core, which might be the mass of several suns, collapses to nuclear density and beyond in fractions of a second. The outer layers of the star, no longer supported from below, crash inward and then rebound in the catastrophic explosion we call a supernova, or, for the most energetic events, a hypernova. What is left at the center, if the progenitor star was massive enough, is a black hole. Roger Penrose imagined what he called a trapped surface, a closed, two-dimensional surface that directed all light rays to an infinitely dense center. This describes what we now call the black hole's singularity. He also used his eponymous Penrose diagrams to show that once such a trapped surface had formed, under general relativity, the collapse toward the singularity is inevitable. The result was a January 1965 paper in Physical Review Letters entitled Gravitational Collapse and Space-Time Singularities. This was the moment the theoretical question transformed. Penrose's theorem, which would eventually earn him the Nobel Prize in Physics in 2020, did not just describe a black hole. It proved that under the assumptions of general relativity, with matter satisfying ordinary energy conditions, the formation of a singularity inside a black hole was not a special case, not a contrived outcome. It was inevitable. Penrose's theorem said roughly this: suppose that a star implodes so far that its gravity becomes strong enough to form an apparent horizon. That is, strong enough to pull outgoing light rays back inward. After this happens, nothing can prevent the gravity from growing so strong that it creates a singularity. Consequently, every black hole must have a singularity inside itself. There it is. The first layer of the revelation. The textbook tells you that a black hole is where gravity is too strong for light to escape. But the theorem underneath that textbook picture is this: once the event horizon forms, something at the center is mathematically required to develop infinite curvature, infinite density, a place where the equations of general relativity produce values that are not merely very large, but literally undefined, a place where known physics ends. The singularity is not an optional feature of the interior. It is a mathematical theorem. But here is what almost nobody tells you about that theorem. It tells us only that a singularity exists. It tells us nothing about what a singularity actually is. The Penrose theorem guarantees geodesic incompleteness, the technical term, which means that paths through space-time simply stop, that some physical trajectories have no continuation past a certain point. But this guarantee says nothing about the physical nature of what lies at that point. It is a theorem about the failure of the mathematical description, not about the presence of a specific physical object. This distinction is not philosophical hair-splitting. It is the entry point to one of the most active and contentious debates in theoretical physics. What does it mean for space-time to have a singularity? Is the singularity a real physical thing? A location with genuinely infinite density? A place where the laws of physics are destroyed? Or is it a signal that general relativity itself is incomplete, that the equations break down because we are applying them outside their domain of validity, and that a more complete theory, one that properly incorporates quantum mechanics, would describe something very different at the center? This is the view held by the large majority of physicists who work on this topic. On this widely shared view, the singularity, as described by general relativity, is almost certainly not a physically real feature of the universe. It is a sign that general relativity reaches its limit of validity somewhere inside a black hole, in the same way that classical thermodynamics reaches its limit when applied to a single atom. The question is, what takes over when general relativity breaks down? What does the correct theory of quantum gravity predict at the center? That question has no agreed-upon answer. We have two extraordinary theories of physics. Both of them have been tested to extraordinary precision within their own domains. Neither of them, individually, can describe what happens inside a black hole. And when we try to combine them, to build what physicists call a theory of quantum gravity, we run into obstacles so profound that some of the greatest minds of the past century have spent their careers trying to surmount them. This is where the journey into a black hole's interior truly begins. Not with the event horizon, not with the drama of infall, not with the popular imagery of a swirling vortex in space. It begins with an epistemological crisis. The recognition that we are standing at the edge of what our physics can say, looking down into a region where our best tools stop working and our best theories start contradicting each other. The event horizon is the door. Beyond it, every step deeper is a step further into territory where certainty dissolves and speculation, careful, rigorous, mathematically disciplined speculation, is the only map we have. A new image from the Event Horizon Telescope collaboration uncovered strong and organized magnetic fields spiraling from the edge of the supermassive black hole Sagittarius A star. And this new view revealed a magnetic field structure strikingly similar to that of the black hole at the center of the M87 galaxy, suggesting that strong magnetic fields may be common to all black holes. The Event Horizon Telescope collaboration, using the technique of very long baseline interferometry at 230 GHz, published the first resolved images of the supermassive black hole at the galactic center, Sagittarius A star, and analyses revealed a bright emission ring associated with the inner accretion flow together with a dark central brightness depression associated with gravitational lensing, redshift, and light capture by the black hole. We can image the environment just outside a black hole. We can trace the orbital paths of stars around the dark mass at the center of the Milky Way with extraordinary precision. We can detect the gravitational waves produced when two black holes collide on the other side of the universe. We can measure the shadow that a black hole casts in the light of its surrounding gas, map the magnetic fields threading through its accretion disk, and test whether the shadow shape matches what general relativity predicts. All of this is the physics of the exterior. All of it stops at the event horizon. Nothing that crosses that boundary can send information back. No experiment, no probe, no observer who descends past the horizon can communicate with the universe outside. This is not merely a technological limitation. It is a fundamental feature of space-time's causal structure. The interior of a black hole is, in a very precise sense, causally disconnected from the rest of the universe. What happens there stays there, not because of any physical barrier, but because the geometry of space-time simply does not permit signals to travel outward from within the event horizon. And yet, physicists believe they can reason about the interior. They believe they can derive constraints on what must be true inside, using principles that apply outside the horizon, principles about quantum mechanics and thermodynamics, and information that must hold universally if our understanding of physics is correct. Those constraints turn out to be extraordinarily demanding, and the deeper you push into the physics, the more the comfortable picture, dense object, singular center, empty space in between, begins to dissolve into something far stranger. This is where we are beginning and where we are going to go. We are going to start at the boundary itself, the event horizon, and understand layer by layer what general relativity tells us about the interior. Then we are going to encounter the quantum, which enters the picture in a way that transforms everything. We are going to meet the people who spent decades arguing about what black holes really do, and trace the extraordinary chain of reasoning that led them to proposals that sound like science fiction, but are, as best we can tell, the most intellectually honest attempts to describe something our instruments will never directly see. The picture that emerges is not tidy. It is not a story with a neat resolution. Some of the deepest questions at the end of this descent into the black hole interior are questions that, with complete honesty, we cannot answer. Not yet, and perhaps not ever. But the attempt to answer them is one of the most extraordinary intellectual adventures in the history of physics. And it begins, as all the best adventures do, with a single step across a threshold that looks unremarkable, a boundary in empty space, invisible, unfelt, and profoundly strange. Step across it now. Pause here, because before we can go any further, it is worth taking stock of where we are and what we have established. We know that a black hole forms when gravity wins, when a mass collapses past its Schwarzschild radius and the event horizon seals around it. We know that the event horizon is not a physical wall, but a causal boundary, unremarkable to an observer falling through it. We know that somewhere inside, general relativity's mathematics demands a singularity, a place where the equations stop producing meaningful values, and where, almost certainly, a more complete theory of physics must take over. And we know that we cannot directly observe any of it. That is the foundation. Now the layers begin. The first layer, just inside the event horizon, is the region that general relativity describes with the greatest confidence. This is the interior of a black hole as classical physics understands it, before quantum effects must be considered. And even here, before anything exotic enters the picture, the physics is more extraordinary than popular accounts suggest. Consider what happens to time. Outside a black hole, time flows in the direction we experience as normal. Forward, from past to future, with the future representing a range of possibilities and the past being fixed. The geometry of space-time outside a black hole, while curved, preserves this basic structure. The time direction and the spatial directions are categorically different. Moving through time and moving through space are related by the geometry of space-time, but they remain, in an important sense, distinct. Inside the event horizon, this distinction collapses. This is one of the most profound and least discussed features of black hole interiors. In the Schwarzschild geometry, the mathematical description of the simplest possible black hole with no rotation and no electric charge. What happens inside the event horizon is that the roles of time and the radial spatial direction are exchanged. Outside the horizon, the time coordinate runs in the time direction, and the radial coordinate runs outward or inward through space. Inside the horizon, these roles switch. The radial direction toward the singularity becomes the time direction. Moving toward the singularity is not moving through space. It is moving through time. This means that, for an observer who has crossed the event horizon, reaching the singularity is not a matter of navigating through space to a particular location. It is a matter of waiting. The singularity lies in their future, just as tomorrow lies in your future. It is unavoidable not because it is spatially inescapable, as if blocked by walls on all sides, but because it is temporally inescapable. You cannot avoid reaching tomorrow, not because you lack the means of going around it, but because tomorrow is a direction in time, and time, in our universe, flows forward. Inside a Schwarzschild black hole, the singularity is that direction. You cannot fly sideways to avoid it. You cannot accelerate in any spatial direction to escape it. Every future-pointing trajectory inside the event horizon reaches the singularity in finite proper time, the time measured on a clock carried by the infalling observer. The mathematics here is unambiguous. The geometry insists on it. The timescale for reaching the singularity after crossing the horizon depends on the mass of the black hole. For a stellar mass black hole with a mass of 10 solar masses, the maximum proper time from the event horizon to the singularity is on the order of microseconds. For a supermassive black hole with a mass of 10 billion solar masses, the same journey takes, at most, on the order of hours. This is not an accident or a curiosity. It follows directly from the Schwarzschild geometry and the fact that the Schwarzschild radius grows linearly with mass. So an astronaut falling into a stellar mass black hole would have perhaps 10 or 20 microseconds of proper time after crossing the event horizon before reaching the singularity. That sounds terrifying, but it needs to be calibrated against what else is happening. For a stellar mass black hole, the tidal forces, the difference in gravitational pull between the astronaut's feet and their head, become lethal long before the event horizon is crossed. The astronaut would be stretched along the radial direction and compressed transversely in the process physicists call, with unfortunate precision, spaghettification. This is not a graceful end. For a supermassive black hole, the tidal forces at the horizon are gentle enough to allow survival. Our hypothetical astronaut, falling into a black hole of the mass of M87's central monster, would not feel lethal tidal stresses at the horizon. They would have hours of proper time inside the black hole before encountering anything destructive. But the singularity still waits in their future, as certain as the end of every finite story. Now let us hold the picture of time and space exchanging roles, because it has an implication that reaches far beyond the fate of hypothetical astronauts. If the radial direction is time-like inside the horizon, if moving toward the singularity is moving through time, then the singularity is not a place in space. It is an event in time. Or more precisely, it is a surface in time, extending across the entire interior. Every observer inside the event horizon, regardless of which direction they move through space, is moving toward the singularity through the dimension that has become temporal. The singularity is the future inside the horizon for everything. This is the interior of the simplest possible black hole, the Schwarzschild solution. And even this idealized case presents us with something that defies ordinary intuition. The real universe, however, does not produce Schwarzschild black holes. Every object in the universe possesses angular momentum. It rotates, even if only slightly. When a star collapses to form a black hole, its angular momentum is conserved. The resulting black hole spins. Real astrophysical black holes are rotating objects, and their mathematical description is not the Schwarzschild solution, but the Kerr solution, derived by the New Zealand mathematician Roy Kerr in 1963. The Kerr solution is, in the view of many physicists, one of the most beautiful mathematical objects in all of physics. It describes a rotating black hole with extraordinary precision, and its interior structure is far more complex than the Schwarzschild case. More complex in ways that are physically consequential and philosophically significant. Take stock of where we are. We have crossed the event horizon, understood how time and space exchange roles inside the simplest black hole, and recognized that the real black holes of the universe are rotating. The Kerr geometry opens up a level of interior structure that the Schwarzschild case does not possess. We are now going to descend into the Kerr solution, into the interior of a real, rotating black hole, and find that the architecture inside is stranger than almost any popular account acknowledges. Begin with what the Kerr solution predicts just outside the event horizon. Between the event horizon and a slightly larger surface called the ergosphere, there is a region of spacetime that has no Schwarzschild analog. The ergosphere is not inside the black hole. An observer can enter the ergosphere and still escape, unlike the event horizon, which permits no escape. But inside the ergosphere, something unusual occurs with the structure of spacetime itself. The rotation of the black hole drags spacetime around with it, a process called frame dragging, predicted by Einstein's general relativity and confirmed observationally for far weaker gravitational fields near Earth by the Gravity Probe B experiment in 2011. In the ergosphere, this frame dragging becomes so extreme that it is impossible for any observer or object to remain stationary with respect to distant stars. The rotation of the black hole physically carries spacetime with it, like water in a vortex carries leaves on its surface. Any observer in the ergosphere, regardless of how powerfully their rockets fire against the rotation, is dragged around the black hole. The ergosphere is named for the Greek word for work, ergon, because the energy stored in the rotation of spacetime here can theoretically be extracted. Roger Penrose showed in 1969 that a particle entering the ergosphere and splitting in two could result in one fragment escaping with more energy than the original particle brought in. with the deficit coming from the black hole's rotational energy. This process, the Penrose process, is not merely a theoretical curiosity. It is now thought to be part of the mechanism that powers the relativistic jets that shoot out of active galactic nuclei, including the enormous jet streaming from M87. There is another reason to pause on the ergosphere before proceeding inside. In 2024, the Event Horizon Telescope collaboration published polarimetric images of Sagittarius A star, and these images show a prominent spiral polarization pattern in the emission ring that is temporally stable, strongly linearly polarized, and dominated by azimuthally symmetric structure. This magnetic field geometry is consistent with what the Kerr solution and magnetohydrodynamic simulations predict for the ergospheric region. The polarization pattern of the light reaching our telescopes carries the imprint of the magnetic fields threading through the innermost region around the spinning black hole, and the theoretical models that include a magnetically arrested disk, a configuration in which strong magnetic fields around a rapidly spinning black hole organize into a coherent structure, match the data well. This is, in the current state of observational science, the closest we can come to peering into the vicinity of a black hole's causal structure. We are watching light that originated in the ergospheric region of a real black hole, shaped by the dragging of space-time by the hole's rotation, lensed and bent by the extreme curvature, and carrying to our telescopes an imprint of the geometry within micro-arc seconds of the event horizon. This is worth naming as a genuine miracle of human ingenuity. A network of telescopes distributed across the Earth, from the Atacama Desert in Chile to the South Pole, was linked together to function as a single Earth-sized telescope. The data was shipped on physical drives because the volume exceeded what the internet could transfer. The resulting images confirmed that what sits at the center of our galaxy is precisely the kind of object general relativity predicts: a spinning mass whose gravity shapes space-time in the exact patterns the Kerr solution demands. And yet, all of this, the shadow, the polarization ring, the magnetic field structure, is exterior physics. It is the physics of the environment surrounding the black hole, the accretion disk and its magnetic fields, the photons completing complex orbits in the extreme curvature before managing to escape to our telescopes. None of it penetrates the interior. The event horizon remains sealed. Now, cross it. Inside the Kerr event horizon, the interior structure differs from the Schwarzschild case in ways that are both beautiful and, in an important sense, deeply problematic for the theory. The Kerr solution possesses not one, but two horizons. The outer horizon is what we have been calling the event horizon, the boundary of no return. But there is also an inner horizon, sometimes called the Cauchy horizon, named after the French mathematician Augustin Louis Cauchy. Between the outer and inner horizons lies a region analogous to the interior of the Schwarzschild black hole, in which the singularity lies inescapably in the future. But once you cross the inner Cauchy horizon, and the mathematics says you can, in principle, reach and cross this second surface, the structure of space-time changes again. Inside the Cauchy horizon, the singularity of the Kerr black hole is not a surface extending across all of the future, as in the Schwarzschild case. It is a ring. The Kerr singularity is a ring of zero radius and infinite curvature, oriented in the plane perpendicular to the rotation axis. And because it is a ring rather than a point, there is, according to the purely classical mathematics of the Kerr solution, a way to pass through its center. The equations suggest that an observer could, in principle, thread through the center of the ring singularity and emerge into a completely different region of spacetime, one that is not causally connected to the exterior in which the black hole sits. This is where the Kerr solution begins to produce results that most physicists believe are mathematical artifacts rather than physical realities. The existence of a stable, traversable path through a rotating black hole interior into a separate region of spacetime is a feature of the exact, ideal Kerr metric, a mathematical solution describing a perfectly stationary, isolated rotating black hole that has existed forever and will exist forever. Real black holes are not like this. Real black holes formed at a specific moment from the collapse of matter, and they interact with their environment. They are perturbed by infalling material, by gravitational waves, by quantum effects. And when physicists study what happens to the Cauchy horizon when even tiny perturbations are introduced, when the idealized isolation of the exact Kerr metric is relaxed, the Cauchy horizon becomes unstable. This was studied rigorously beginning in the late 1960s and 1970s by physicists including Werner Israel, and later Eric Poisson and Werner Israel together in the 1990s, who demonstrated what became known as mass inflation. When an observer approaches the Cauchy horizon inside a Kerr black hole, the infalling and outgoing radiation that has crossed the outer horizon piles up at the Cauchy horizon, blue-shifted to arbitrarily high energies. The energy density at the Cauchy horizon diverges. It becomes infinite. This is not a naked singularity in the usual sense, but it means that the Cauchy horizon in a realistic, perturbed black hole is not a gentle surface you can simply cross. The mathematical singularity, which in the ideal Kerr metric is confined to the ring and passable, spreads to the Cauchy horizon in any realistic scenario. Some researchers argue this means the true singularity structure of a real rotating black hole is more like a singular surface at the Cauchy horizon, not a ring singularity further inside. Others think that quantum effects will intervene before the mass inflation singularity develops fully. What is not disputed is that the clean, navigable interior of the ideal Kerr metric almost certainly does not represent the actual interior of any real black hole that ever formed in our universe. This instability of the Cauchy horizon is one of the places where Penrose's cosmic censorship conjecture becomes relevant. Penrose conjectured, and it remains a conjecture, not a proven theorem, that singularities inside black holes are always hidden behind horizons, always causally shielded from the exterior universe. This is cosmic censorship. The singularity cannot be seen or interacted with from outside the black hole. The instability of the Cauchy horizon, turning it into a singular surface, is in some ways consistent with this conjecture. The singularity is still inside the black hole, still behind the outer event horizon. But the detailed geometry of the interior that the conjecture implies is far more complex and contentious than any simple picture conveys. What we have at this stage is a picture of the black hole interior that can be summarized as follows. General relativity, applied to the simplest idealized cases, gives us a clear account of the outer region, the event horizon, the ergosphere, the region between the outer and inner horizons. It gives us, for the rotating case, a prediction of a second horizon, a ring singularity, and a mathematically fascinating but physically suspect extended geometry. When we move beyond the idealizations and consider realistic perturbations, even the classical picture becomes unstable, with singularities developing in places the ideal solution did not predict. All of this is classical. It does not yet incorporate the quantum. The quantum changes everything. In 1974, Stephen Hawking published a short paper in the journal Nature titled Black Hole Explosions. The title's question mark was genuine. The idea was, by his own account, something he had not expected, and that alarmed him when he first derived it. By applying quantum field theory to the curved spacetime around a black hole, Hawking showed that the event horizon is not absolutely dark. Pairs of virtual particles born near the horizon can be separated. One falls inward through the horizon, the other escapes outward as real radiation. The event horizon in quantum field theory has a temperature. Black holes radiate. The temperature of this radiation is inversely proportional to the mass. For a black hole with the mass of the Sun, the temperature is only 10 to the -7 Kelvin, negligible compared to the 2.7 Kelvin cosmic microwave background. No stellar black hole can evaporate in any observable sense today. A solar mass black hole would require roughly 10 to 67 years for complete evaporation, a timescale trillions upon trillions of times longer than the current age of the universe. But the theoretical implication is seismic. If black holes radiate, they lose mass. If they lose mass, they eventually evaporate entirely. And Hawking's calculation showed that the radiation emitted is precisely thermal. It carries no information about what fell into the black hole beyond the mass, charge, and angular momentum. A black hole formed from collapsed hydrogen atoms radiates identically to a black hole formed from collapsed photons, if both have the same mass. Two completely different initial objects with the same mass would produce identical radiation, and the information about their difference would be lost along with the black hole. This is the information paradox. It was there from the very beginning of Hawking's discovery. The core of the problem: if a black hole forms from matter collapsing in a pure quantum state and evaporates completely through thermal radiation, the final state will be a mixed state. This violates unitarity, the fundamental principle that quantum evolution is always reversible, that information is never destroyed. Hawking himself, for decades, believed that black hole evaporation genuinely destroyed information, that quantum mechanics needed to be modified in the presence of strong gravity. Most other physicists, particularly those working in string theory, believed that Hawking's semi-classical calculation was missing something, that information was somehow preserved but hidden in correlations between Hawking quanta that the simple calculation did not account for. The debate was not merely philosophical. It pitted two pillars of fundamental physics against each other directly. If information is lost in black hole evaporation, then quantum mechanics is violated. One of the most precisely tested theories in the history of science breaks down in the presence of black holes. If information is not lost, then Hawking's calculation must be wrong or incomplete in a way that, given how careful and well-founded the calculation was, implies something profound about the nature of the black hole interior that classical general relativity completely misses. Don Page, a student of Hawking, made a pivotal observation in 1993. He showed that if evaporation is unitary, if information is truly preserved, then the entropy of the Hawking radiation must behave in a specific way over the lifetime of the black hole. It should rise as radiation is emitted in the early stages, then decrease as the black hole loses mass and the radiation begins to carry information about the interior, tracing a curve that became known as the Page curve. Hawking's original calculation predicted monotonically increasing entropy, which, by Page's argument, was impossible if unitarity held. But early Hawking radiation and late Hawking radiation showed no correlation in the simple semi-classical picture. How could the radiation know, at late times, what had been absorbed early on? The information was locked behind the event horizon. There was no obvious mechanism for it to escape. There is, in theory, a a straightforward answer to this. The information is encoded in the outgoing Hawking radiation in subtle quantum correlations that are too small for any simple calculation to see, but are there nonetheless. This is the answer that most string theorists favored, based on the logic that black holes, being quantum objects, must obey quantum mechanics. The ADS/CFT correspondence, proposed by Juan Maldacena in 1997, provided strong theoretical evidence that this had to be the case. It demonstrated a mathematical equivalence between a theory of quantum gravity in a certain space-time geometry and an ordinary quantum field theory on the boundary of that space-time. And the boundary theory was manifestly unitary, preserving information completely. But the question of mechanism remained. How precisely does the information get out? What is the physical process by which information about the interior of a black hole, sealed behind an event horizon, causally disconnected from the outside, finds its way into the outgoing radiation? This question became the entry point for one of the most dramatic episodes in theoretical physics of the 21st century. In 2012, the physicists Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, collectively known by the acronym AMPS, published an argument that revealed a deep tension at the heart of the information problem. Their firewall paper, which first appeared on the Archive preprint server in July of that year, began with an apparently modest goal: to demonstrate that a particular proposed resolution to the information paradox, called black hole complementarity, was internally inconsistent. Black hole complementarity had been the favored framework for preserving unitarity without modifying the interior experience. Its logic went like this. An observer outside the black hole sees information encoded in the Hawking radiation. An observer falling through the event horizon sees the interior without any drama. But these two observers cannot compare notes. The infalling observer cannot send a signal back out, so there is no contradiction, even if both pictures are simultaneously true. The information is out there and also in there, but the principle that no single observer can ever see both means there is no measurable paradox. AMPS pointed out a problem with this logic. Unitarity requires that, for an old enough black hole, one that has emitted more than half its original mass in Hawking radiation, any outgoing particle of Hawking radiation will be strongly entangled with the earlier Hawking radiation. However, quantum field theory in curved spacetime requires that this same outgoing Hawking particle is entangled with its partner still inside the event horizon. This is what produces the Hawking radiation in the first place, the pairing of particles across the horizon. But quantum entanglement obeys a strict rule called monogamy. A quantum system can be maximally entangled with only one other system. A single outgoing Hawking particle cannot be maximally entangled with both the early Hawking radiation and its interior partners simultaneously. One of these entanglements must be broken. If the entanglement between the outgoing particle and its interior partner is broken, the gentle vacuum of quantum field theory at the horizon is replaced with something else entirely. Breaking the entanglement releases energy. Specifically, it releases a wall of energetic quanta right at the event horizon, what AMPS called a firewall. The firewall would incinerate any infalling observer the moment they crossed the event horizon. It is not just a minor perturbation. It is a complete destruction of the smooth, unremarkable crossing that general relativity predicts. The use of a firewall to resolve this inconsistency remains deeply controversial, with physicists divided as to the solution to the paradox. The firewall resolution requires a violation of Einstein's equivalence principle, the foundational principle that free falling is indistinguishable from floating in empty space. If a firewall burns the infalling observer, then the event horizon is locally detectable, which contradicts everything general relativity tells us about the causal structure of black holes. This is the three-way conflict at the heart of the firewall paradox. Unitarity says information is preserved. Quantum field theory says entanglement pairs across the horizon must be present. Monogamy of entanglement says they cannot all coexist. Something has to give. But each of the three principles that is threatened is one of the deepest and most well-tested ideas in physics. Sacrificing any one of them demands an explanation for why the sacrifice is justified, and why every experiment that has tested the sacrificed principle was testing it in a domain where the violation was too small to detect. Some researchers suggest that the entanglement must somehow get immediately broken between the infalling particle and the outgoing particle, producing the firewall. Others argue that such violations of locality cannot resolve the paradox. Juan Maldacena and Leonard Susskind proposed in 2013, the same year as the full firewall paper publication, that the outgoing and infalling particles are connected by wormholes, a conjecture sometimes written as the equation ER equals EPR, linking Einstein-Rosen bridges, wormholes, to Einstein-Podolsky-Rosen pairs, entangled particles. In this picture, the entanglement between the outgoing Hawking particle and its interior partner is not a simple quantum correlation, but a wormhole, a microscopic geometric connection through space-time that preserves the monogamy of entanglement without requiring a firewall. The fuzzball picture, developed from string theory by Samir Mathur and collaborators beginning in the early 2000s, takes a different approach. It proposes that the interior of a black hole is not empty space with a singularity at the center. Instead, the entire volume of the black hole is filled with a quantum string configuration, a fuzzball, in which there is no event horizon, no interior vacuum, no singularity. The event horizon is replaced by a fuzzy quantum surface that radiates information back out as string excitations. In this picture, the smooth interior of general relativity is entirely an illusion, and the firewall problem dissolves because there is no interior to be burned in. The information paradox remains an active field of research in quantum gravity. It is now generally believed by most researchers that information is preserved in black hole evaporation. But views differ profoundly as to precisely how Hawking's original semi-classical calculation should be corrected, and what the mechanism of information preservation implies about the interior. In 2019, building on the island formula and concepts from holography, physicists including Netta Engelhardt and Ahmed Almhiri succeeded in deriving the Page curve, the curve that a unitary evaporation process requires, from a semi-classical calculation that included contributions from island regions in the interior of the black hole. Their approach showed that there exists a different semi-classical analysis from Hawking's that yields the Page curve, and while the calculation was within the regime of semi-classical gravity, the rules for computing certain quantities were vastly different from the standard rules. The island formula effectively showed that, at late times in the evaporation process, the entropy of the Hawking radiation should be computed by including a region inside the black hole, the island, in the calculation of the radiation's entanglement, entropy. This was a significant result. It demonstrated in a controlled theoretical setting that the Page curve can be derived without assuming quantum gravity in its full complexity, using only semi-classical tools augmented by insights from holography and the ADS/CFT correspondence. Developments such as the island formula, quantum extremal surfaces, and holography have transformed the understanding of black hole evaporation. The island formula provides a possible explanation to the information problem by a new mechanism for information retrieval. We arrive at a unitary page curve via the island formula, a gravitational fine-grained entropy formula for the Hawking radiation. But the island formula, while mathematically compelling, raises its own deep questions. The island region appears inside the black hole. The Hawking radiation outside is entangled with degrees of freedom inside the island. This entanglement is the mechanism by which information escapes. But the island is behind the event horizon. How can information on the island influence the radiation outside the horizon if nothing can travel from inside to outside? The answer, insofar as there is one that most physicists would accept, involves the idea that entanglement is not a signal. Quantum entanglement allows correlations between distant systems without allowing information to be transmitted between them faster than light. The information is not sent from the island to the radiation. It is encoded in the correlations between them from the moment they were created. The event horizon does not prevent entanglement, only classical signals. Quantum correlations can, in a sense, span the horizon without violating causality, because they carry no classical information on their own. But even this answer leaves the deeper question untouched. What is actually happening inside the black hole? What is the physical substrate of the island? What does the interior look like in the correct quantum theory of gravity? We are not done descending. We have passed through the event horizon, tracked the exchange of time and space roles inside, understood the difference between the Schwarzschild and Kerr interiors, met the singularity theorems and their limitations, grasped the Hawking radiation and the information paradox, and now stand at the edge of the quantum gravity regime, the innermost layer, where no existing theory is adequate, where the most honest thing we can say is that we do not know, and where the proposals for what might be true range from the beautiful to the philosophically vertiginous. The next steps take us deeper. Picture yourself suspended in absolute darkness, not the darkness of a closed room where your eyes adjust and shapes slowly emerge, but a darkness in which the concept of a shape has lost its meaning. There is no surface to touch. There is no temperature to feel in the ordinary sense. The space around you is not empty in the familiar way. It seethes with quantum activity at scales far below anything detectable by the instruments you carry. You are deep inside a black hole, somewhere between the event horizon and the center. General relativity brought you here. Quantum mechanics is about to tell you that the place you are standing may not be what it appears. We have established the classical picture and the quantum problem. Now we go deeper into the proposals, the specific, mathematically grounded ideas that physicists have developed to describe what actually exists inside a black hole's interior when quantum mechanics is properly incorporated. These are not wild speculations. They are constrained theories, derived from principles, tested against mathematical consistency, argued over in the physics literature with extraordinary rigor. None of them is proven. Several of them cannot be proven by any experiment we can currently conceive of. But they represent the best thinking of the best minds, working on what is arguably the hardest problem in fundamental physics. Each proposal gives a different answer to the question of what you would find if you could somehow descend all the way to the center of a black hole. Each one implies a different fate for the information that falls in. Each one requires abandoning something we thought we knew. The first proposal we need to examine carefully is the one that general relativity itself offers, unmodified by quantum corrections. This is not merely the naive textbook version. It is a rigorous, mathematically careful description of what the field equations of general relativity actually predict in the interior. And it is worth spending time here because the departures from this picture, when they come, will be all the more striking. In the general relativistic picture, the interior of a Schwarzschild black hole is a volume of space-time in which the singularity lies in the absolute future of every infalling observer. The space-time geometry between the horizon and the singularity is curved, but it is smooth and well-defined at every point, except the singularity itself. There are no walls, no visible boundaries, no regions of extraordinary particle density through which the infalling observer must pass before reaching the singularity. The journey from the horizon to the singularity, for an observer in free fall, is a journey through space-time that looks and feels locally normal, just as the horizon crossing did. Locally, at every point short of the singularity itself, the laws of physics appear to hold in their usual form. This is the general relativistic prediction, stated carefully. The interior of a black hole is geometrically smooth everywhere except at the singularity. The singularity is space-like in the Schwarzschild case, lying across the future of all infalling observers, like a wall across time rather than a point in space. And the singularity itself is a boundary of the space-time, a place where the manifold ends, where there is no further future, where the smooth geometry terminates. Everyone knows that a black hole has a singularity at the center. The textbook description says it is a point of infinite density where gravity becomes infinitely strong. You probably think of it as a location, a place in space, like the center of the Earth, that you approach and eventually reach. That picture is almost entirely wrong. The singularity of a Schwarzschild black hole is not a point. It is not a location in space. It is a moment in time, a space-like surface extending across the entire interior, as real and universal in the black hole interior as tomorrow is in your universe. There is no spatial direction you can move to avoid it. It is not over to the left or below you. It is ahead of you in time, and every path through the interior reaches it in finite duration. The singularity is not like the center of the Earth. It is more like the end of the universe, not a place you approach, but a moment you reach. And here is what that means in practice. An observer inside the event horizon cannot stand still, cannot hover, cannot choose to stay at a fixed distance from the singularity. Just as you cannot choose to remain at this exact moment in time, right now you are already being carried forward into the next moment. An observer inside a black hole is being carried forward into the singularity, not because they are falling, not because gravity is accelerating them, because the geometry of space-time itself, inside the horizon, makes the future point inward, and the singularity is the end of that future. This is the general relativistic picture, taken seriously on its own terms. It is strange enough. Now the quantum enters. The quantum theory of fields in curved space-time, the framework Hawking used in 1974, makes a prediction that is independent of the information paradox, independent of the firewall debate, and deeply relevant to what the interior of a black hole is like, even before you approach the singularity. That prediction involves the nature of the quantum vacuum, and it leads to a phenomenon that affects the structure of the interior in ways the classical picture entirely misses. To understand this, we need to understand what the quantum vacuum actually is. In ordinary flat spacetime, the spacetime of special relativity without gravity, the quantum vacuum is a specific, well-defined state of quantum fields. It is not empty in the sense of containing nothing. It is the lowest energy state of a quantum field, a state defined by the absence of real particles. But it is filled with quantum fluctuations, transient disturbances in the field that are constantly creating and annihilating pairs of virtual particles. This activity has real, measurable consequences. The Casimir effect, the Lamb shift in hydrogen energy levels, the anomalous magnetic moment of the electron, all of which have been measured and confirmed to extraordinary precision. The vacuum state, however, depends on how you define energy, and how you define energy depends on how you define time. In flat spacetime, all inertial observers agree on what positive energy and negative energy means, so they all agree on what the vacuum is. Accelerated observers do not. This is the Unruh effect, discovered by William Unruh in 1976. An observer accelerating through the vacuum of flat spacetime detects a thermal bath of particles, while an inertial observer in the same region detects nothing. The vacuum state defined by the inertial observer is not the vacuum state seen by the accelerated observer. Near a black hole, where spacetime is curved, this observer dependence of the vacuum state has profound consequences. The quantum field theory near a black hole has no single, universally agreed upon vacuum state that all observers share. An observer far from the black hole defines their vacuum in terms of their time coordinate, which is the ordinary time coordinate of the distant universe. An observer, in falling through the horizon, defines their vacuum in terms of their proper time, which near the horizon is related to the distant time coordinate by an exponential transformation. These two vacua are not the same. The infalling observer's vacuum, the state they would describe as empty, containing no particles, is, when described in terms of the distant observer's coordinates, a state full of particles. The Hawking radiation is exactly the expression of this discrepancy. The distant observer sees particles where the infalling observer sees vacuum. Both descriptions are correct in their own reference frame. The particle content of the quantum field is not an observer-independent fact. Stay with this, because it is one of the deepest ideas in the story of black hole interiors. The interior of a black hole, as described by quantum field theory in curved spacetime, is not merely a classical geometry that contains matter. It is a quantum system whose very particle content depends on who is describing it. An infalling observer, crossing the event horizon of a large black hole, sees around them the vacuum, smooth, empty, undisturbed quantum fields. That same region of spacetime described from the outside is filled with Hawking radiation and with the entangled interior partners of the outgoing Hawking quanta. These two descriptions both reflect aspects of reality, but they are not simultaneously accessible to any single observer. The infalling observer cannot, while inside the black hole, verify that their surroundings look like vacuum to outside observers. The outside observer cannot, by any measurement accessible to them, confirm what the infalling observer experiences inside. This is why the firewall paradox cuts so deep. It arises precisely because of the question of which description is correct at the horizon. If you take the outside observer descriptions seriously, if you insist that the entanglement structure of the Hawking radiation, as seen from outside, must somehow be preserved, and that this entanglement must break with the interior partner, then the infalling observer must encounter not a vacuum at the horizon, but a wall of radiation that the outside description insists must be there. The smooth interior of the infalling observer's experience is incompatible with the unitary radiation catalogue of the distant observer. One of the most carefully developed proposals for resolving this tension is the idea that the apparent contradiction arises from treating the black hole interior as an independent region of spacetime, when in fact it is not. This is the central insight of what is sometimes called the holographic principle and its application to black hole interiors. The holographic principle emerged from work by Jacob Bekenstein in the early 1970s and was formalized as a principle by Gerard 't Hooft and Leonard Susskind in the 1990s. Bekenstein noticed something extraordinary about black hole entropy. In thermodynamics, the entropy of a system is typically an extensive quantity. It scales with the volume of the system. More material, more entropy. But the entropy of a black hole, as Bekenstein showed in 1973, is proportional not to the volume of the black hole, but to the area of its event horizon. Specifically, the entropy is equal to 1/4 of the horizon area measured in Planck units, the smallest physically meaningful unit of area in quantum gravity. This was the Bekenstein-Hawking entropy. Formula S equals A over 4, where A is the horizon area in Planck units. The formula has since been confirmed in multiple contexts, derived from string theory and loop quantum gravity approaches, and is considered one of the most reliable results in quantum gravity, not because it is directly testable, but because it has been derived from so many different angles that all of them pointing to the same answer is itself strong evidence. The area scaling of black hole entropy implies something profound. If entropy measures the number of possible states of a system, the information content of the system, then the information inside a black hole is proportional to its surface area, not its volume. This suggests that the interior degrees of freedom of a black hole are not independent of the surface. The boundary contains all the information about the interior. The holographic principle generalizes this idea to all of physics. The information content of any region of space is encoded on the boundary of that region, not in the volume. Applied to black holes, this principle suggests that the interior of a black hole is not an independent reality that must be separately described. It is encoded in the quantum state of the event horizon and the radiation emitted from it. The interior is, in some sense, a derived picture, a reconstruction from the boundary data, rather than a fundamental standalone space-time region. This is a profound departure from the usual picture of space-time as a collection of independent locations, each with its own local reality. If holography is correct, then asking what is independently happening inside the black hole, as if the interior were a region whose properties are simply there, regardless of external description, is asking the wrong question. The interior properties are not primary. They are secondary, derived from the entanglement structure of the Hawking radiation, accessible in principle to an observer who has gathered and processed all of the radiation. The Maldacena conjecture, the ADS/CFT correspondence, first proposed by Juan Maldacena in 1997, provided the first concrete mathematical realization of holography. It demonstrated an exact equivalence between a theory of quantum gravity in an anti-de Sitter spacetime, a universe with a specific kind of negative cosmological constant, and a conformal field theory living on the boundary of that spacetime, with no gravity at all. The boundary theory is manifestly unitary, meaning it preserves information exactly. Since the two theories are equivalent, the gravitational theory must also preserve information, even though the bulk description, the interior spacetime, suggests otherwise from the Hawking radiation argument. This equivalence does not directly tell us what the interior of a black hole looks like. It tells us that whatever the interior looks like, it must be consistent with a unitary description on the boundary. The interior is constrained by the exterior, but the detailed map between the boundary description and the interior description, what physicists call the bulk-to-boundary map, or more specifically the interior reconstruction, is not fully understood. Some researchers think they have partial answers. Others think the question is deeper than any partial answer captures. Now let us descend to a scale where the proposals diverge most dramatically, to the vicinity of the singularity itself, or rather, to the place where the singularity would be if general relativity were correct. The approaches to quantum gravity that have been most developed, string theory and loop quantum gravity, give different answers about what replaces the singularity when quantum effects are fully incorporated. In string theory, the fundamental objects are not point particles, but one-dimensional strings whose vibration modes produce the diverse spectrum of particles we observe. The earliest length scale at which the point particle description of general relativity must break down is the string scale, which is close to but not identical to the Planck scale. String theory suggests that as you approach the singularity, as the curvature of space-time grows to string scale levels, the ordinary smooth geometry of general relativity dissolves into a different kind of structure. In some string-theoretic descriptions, the singularity is resolved into a smooth transition to a different space-time geometry. In others, the singularity region is replaced by a complicated stringy topology with no classical geometric description at all. One of the most striking string-theoretic proposals for the black hole interior is the fuzzball, which we encountered briefly earlier and which deserves more careful treatment. In string theory, a black hole is not actually a smooth space-time geometry with a singularity at the center and empty space throughout the interior. Instead, the quantum string states that make up the black hole, the microstates that account for the Bekenstein-Hawking entropy, are fuzzballs, horizon-size objects in which the entire volume is occupied by a quantum string configuration. There is no interior. There is no singularity. There is no empty space-time within the event horizon. The fuzzball fills the whole volume out to the horizon, radiating information through ordinary quantum processes. The fuzzball proposal is physically striking for several reasons. First, it dissolves the information paradox entirely. Information is never lost behind a horizon because there is no interior space to hide it in. The radiation from a fuzzball is not thermal Hawking radiation. It is ordinary quantum radiation that carries information about the initial state. Second, it is computationally derived from string theory in specific low-dimensional cases. For certain supersymmetric black holes, idealized objects with specific quantum numbers, Samir Mathur and collaborators have explicitly constructed the fuzzball microstates and shown that they reproduce the Bekenstein-Hawking entropy formula. The difficulty is in extending this picture to astrophysically realistic black holes, large non-supersymmetric objects, where the technical machinery of fuzzball construction is far less developed. Some researchers argue that the fuzzball picture applies universally, and that the smooth interior description is simply a coarse-grained approximation that breaks down when quantum effects are taken into account, even near the horizon of a large black hole. Others argue that fuzzball-like effects are negligibly small near the horizon of a macroscopic black hole, and that the smooth classical interior remains a good description throughout most of the region between the horizon and the singularity, with quantum corrections becoming important only very close to the singularity. Loop quantum gravity, the other major approach to quantizing spacetime, offers a different picture. In loop quantum gravity, developed in its modern form by Abhay Ashtekar, Carlo Rovelli, Lee Smolin, and others beginning in the late 1980s, spacetime itself is quantized. The geometry of space is not a smooth, continuous fabric, but a network of quantum relationships, a spin network, in which the areas and volumes of regions take discrete, quantized values. The Planck scale is the scale at which this discrete structure becomes relevant. Applied to the black hole interior, loop quantum cosmology, the cosmological version of the framework, which applies the same principles to regions of strong curvature, suggests that the singularity is not reached. As the curvature grows toward the Planck scale, the quantum geometry produces a repulsive effect that prevents infinite density from developing. The singularity is replaced by a quantum bounce, a region of extreme but finite density beyond which the spacetime continues, either into a collapsing then re-expanding geometry or into a new region of spacetime on the other side. This bounce picture is mathematically appealing. It avoids the boundary of spacetime that the singularity represents. It gives the infalling observer a continuation of their trajectory past the point where classical physics breaks down. But it raises its own questions. What is on the other side of the bounce? Where does the new spacetime region connect to the original exterior? Could it connect to a white hole, a time-reversed black hole, a region from which matter can only exit, never enter? Some physicists, including Carlo Rovelli and collaborators in work published through the 2000s and 10s, have proposed exactly this: that the inside of a black hole, after the quantum bounce at the Planck scale, connects to a white hole. The entire black hole-white hole system would form a self-contained, sealed-off bubble in spacetime, with matter falling in from one end and eventually emerging from the other. The black hole would appear to evaporate from the outside through Hawking radiation, but the information would survive inside the bounced geometry, eventually re-emerging through the white hole exit. This proposal is mathematically interesting, but observationally inaccessible in any direct sense. And its relationship to the information paradox, the page curve, and the holographic constraints remains an area of active investigation and genuine disagreement. There is a theme running through all of these proposals: string theory, fuzzballs, loop quantum gravity, holographic reconstruction, island formulas. And it is this: the deeper you go into the black hole, the more the concept of a definite, observer-independent interior becomes problematic. Every serious attempt to reconcile the quantum with gravity inside a black hole ends up suggesting that the interior spacetime, as classically conceived, is not fundamental. It is either a coarse-grained description that breaks down at the quantum level, or an approximate reconstruction from boundary data, or a geometric description that fails entirely at the Planck scale and must be replaced by something discretized or stringy or holographic. No proposal leaves the classical interior intact and simply adds a small correction. This is significant. The message of quantum gravity research applied to black holes is not that the interior is mostly as general relativity describes, with a small quantum correction near the singularity. The message is that the interior, as a concept, is under assault at a fundamental level, and that the picture we get of it depends profoundly on which principles of physics we choose to prioritize when they conflict. This is where we arrive at one of the deepest questions in the entire enterprise. And to frame it properly, we need to spend time with an idea that, when you first encounter it, sounds more like a philosophical riddle than a physics result. The idea is called black hole complementarity, and it was developed in the early 1990s by Leonard Susskind, Larus Thorlatius, and John Uglum. It grew directly out of the Hawking radiation problem and the tension between the outside and inside observer descriptions. The proposal was this: there is no single observer-independent description of what happens to information in a black hole. An observer outside the black hole sees the infalling matter pile up and smear across the horizon as Hawking radiation, with all the information eventually encoded in the outgoing radiation. An observer falling through the horizon sees the interior spacetime, smooth and uneventful, with the matter passing through and heading toward the singularity. Both descriptions are internally consistent. Both are accurate for the observer to whom they apply, and no single observer ever has access to both descriptions simultaneously. The outside observer who tries to verify what the infalling observer experienced inside must wait for all the Hawking radiation to be emitted, which takes longer than the age of the universe for a stellar mass black hole. By that time, the infalling observer has long since reached the singularity. The infalling observer inside the black hole cannot send information about their interior experience back out. The two descriptions are complementary in the quantum mechanical sense, mutually exclusive, but both required for a complete description of the system, like the wave and particle descriptions of a quantum particle. This complementarity was proposed as the resolution. We stop demanding a single objective description of the interior and accept that the interior is in some sense a frame-dependent concept. What the interior contains depends on the reference frame of the observer describing it, just as simultaneity in special relativity depends on the reference frame of the observer measuring it. The firewall argument demolished the naive version of this resolution. AMPS showed that if unitarity requires the late Hawking radiation to be entangled with the early radiation, which it does, and if quantum field theory requires the outgoing particle to be entangled with its interior partner, which it does, then the two demands are incompatible, regardless of the observer. The contradiction does not depend on a single observer accessing both descriptions. It is a logical contradiction within the consistency requirements of the theory itself. And yet, the deeper spirit of complementarity, the idea that the interior is not a primary observer-independent reality, but a derived description, has survived the firewall and continues to inform the best current thinking. The island formula, the holographic reconstruction of the interior, the entanglement wedge reconstruction. All of these can be seen as ways of making complementarity precise, of specifying exactly which degrees of freedom describe the interior and how they relate to the exterior description. The entanglement wedge reconstruction, developed by several groups through the 2000s and building on the Ryu-Takayanagi formula that Shinsei Ryu and Tadashi Takayanagi proposed in 2006, offers perhaps the most concrete current picture of how the interior relates to the exterior. The Ryu-Takayanagi formula provides a way to compute the entanglement entropy of a region in a holographic theory by computing the area of a specific minimal surface in the bulk spacetime. The entanglement wedge is the bulk region associated with a boundary region, and a key theorem, the entanglement wedge reconstruction theorem, states that any bulk operator in the entanglement wedge of a boundary region can, in principle, be reconstructed from the boundary region alone. For the early stages of black hole evaporation, before the page time, when less than half the black hole has evaporated, the entanglement wedge of the outside radiation does not include the black hole interior. The interior is not accessible from the outside data. For the late stages, after the page time, when more than half the black hole has evaporated, the entanglement wedge of the outside radiation expands to include a portion of the black hole interior, the island region. The interior becomes accessible from the outside data, in principle. This is the island formula in geometric language. Before the page time, the interior is genuinely inaccessible from outside. After the page time, the interior is, at least partially, encoded in the outside radiation. The transition between these regimes is the page time, the halfway point in the evaporation. And it is at this transition that the entropy of the Hawking radiation stops increasing and begins to decrease, tracing the page curve that unitary evolution demands. The picture that emerges is not of an interior that has always been secretly connected to the outside. It is of an interior whose connectivity to the outside changes over time, as the black hole evaporates, as the entanglement structure of the Hawking radiation builds up, as the island region inside the black hole gradually becomes encoded in the radiation outside. This is a fundamentally different picture from classical general relativity. In the classical picture, the interior is always causally disconnected from the exterior. The causal barrier of the event horizon is permanent and absolute. In the quantum picture suggested by the island formula and holographic reconstruction, the interior is causally disconnected in the classical sense, but quantum mechanically accessible through entanglement. And this accessibility grows with time as the black hole evaporates. The question of what this means physically, what it implies about the experience of an observer inside the black hole, what it says about the structure of space-time at a fundamental level, is not settled. Some researchers interpret the island formula as telling us that the space-time geometry inside a black hole, in the late stages of evaporation, is radically different from what general relativity describes, perhaps involving replica wormholes connecting the interior island to the exterior radiation. Others interpret it more conservatively, as a calculational tool that gives the right entropy without necessarily implying a specific geometric picture of the interior. These interpretive questions are not merely academic. They bear on one of the most fundamental issues in physics, whether space-time geometry is a fundamental feature of reality or an emergent, approximate description that breaks down when quantum effects become important. The black hole interior, where the quantum and gravitational effects are most extreme, is the natural laboratory for this question. It is the place where the answer, if found, would resonate through every corner of fundamental physics. And this is where we pause at the edge of the deepest territory. We have descended from the event horizon through the classical interior of general relativity, through the Hawking radiation and the information paradox, through the firewall crisis and its proposed resolutions, through the holographic principle and the island formula. Each layer has revealed a reality stranger than the one before. The deepest layer is ahead. Stand in a desert at night, far from any city, and turn your face upward. The stars you can see are individual suns, each one a nuclear furnace sustaining itself against the inward pull of its own gravity. Every one of them will eventually end. Some will become black holes. And every black hole that forms carries within it a question that no human instrument can answer directly, that no signal from the interior can ever confirm, but that the logic of physics demands we confront with complete honesty. That question is this: what, precisely, is the nature of the structure that replaces the singularity when quantum mechanics is properly applied? And the deeper question beneath it: what does the answer tell us about the nature of space-time itself? We have established the landscape. General relativity predicts a smooth interior, terminating in a singularity. Quantum field theory in curved space-time predicts Hawking radiation and an information paradox. The firewall argument reveals a three-way conflict between unitarity, quantum field theory, and the equivalence principle. The island formula offers a mathematical resolution that reproduces the page curve. Holography suggests the interior is, in some sense, encoded on the boundary. Various quantum gravity proposals, fuzzballs, loop quantum bounce, stringy resolution, each offer a different picture of what replaces the singularity. What we have not yet done is follow each of these threads to their endpoint, to the specific, concrete prediction each one makes about what a sufficiently advanced traveler would actually encounter if they could somehow descend to the center of a black hole, past the point where any existing theory can be trusted, into the region where the answer must involve a full theory of quantum gravity that we do not yet possess. That region begins at a length scale called the Planck length, and it is worth establishing what this length scale means before proceeding. The Planck length is derived from three fundamental constants: Newton's gravitational constant, Planck's constant from quantum mechanics, and the speed of light. Combining these three constants in the only dimensionally consistent way produces a length of approximately 1.6 times 10 to the negative 35 meters. This is not an arbitrary scale. It is the scale at which the quantum fluctuations in the geometry of spacetime itself become of order 1. The scale at which you cannot measure a distance without creating a black hole. The scale at which the smooth fabric of spacetime dissolves into quantum uncertainty. To put this in perspective, the Planck length is to a proton what a proton is to a distance of about 100 million kilometers, roughly the distance from the Earth to the Sun. The ratio between the Planck length and the size of a proton is approximately 10 to the 20, the same ratio as between a proton and the Earth-Sun distance. The Planck scale is not merely small. It is so many orders of magnitude smaller than anything we have directly probed that the gap between our best experimental reach and the Planck scale is larger than the gap between a proton and a macroscopic object. The density at which Planck scale physics becomes relevant, the Planck density, roughly 5 times 10 to the 96 kilograms per cubic meter, is so far beyond anything producible in any laboratory that direct experimental access to Planck scale physics will, in all likelihood, remain impossible for the foreseeable future of human civilization. We reason about this regime from indirect evidence, from mathematical consistency, from the logic of theoretical constraints. And inside a black hole, the Planck scale is reached. Whether it is reached at the singularity, near the singularity, or at the Cauchy horizon depends on the proposal. But every serious quantum gravity approach agrees that the Planck scale is not merely relevant inside a black hole. It is unavoidable. The black hole interior is the only place in the current universe, aside from the initial moments of the Big Bang, where Planck scale physics is a certainty rather than a speculation. This is the scale at which we must now work. Consider the Schwarzschild interior first, in the context of loop quantum gravity. The loop quantum gravity approach quantizes spacetime geometry directly, treating the area and volume of regions not as smooth, continuous variables, but as operators with discrete spectra, specific quantized values that the geometry can take, separated by gaps at the Planck scale. The fundamental quanta of geometry in loop quantum gravity are called spin networks, and the dynamics of these networks as they evolve in time is described by what are called spin foams, a four-dimensional generalization of the two-dimensional foam structure that the networks trace out in time. When loop quantum cosmology, the application of these techniques to highly symmetric spacetimes, including the interior of a Schwarzschild black hole, is applied to the singularity region, the result is consistent across multiple analyses. The curvature does not grow to infinity. As the collapsing geometry approaches the Planck density, the discrete structure of spacetime generates a quantum pressure, an effective repulsive force that has no classical analog, which halts the collapse and reverses it. The singularity is replaced by a quantum bounce. After the bounce, the geometry expands. What was a collapsing spacetime region becomes an expanding one. The question of where this expanding region connects to is answered differently by different researchers in the loop quantum gravity community. But one prominent proposal is that it connects to a white hole region. The black hole, from the outside, appears to evaporate through Hawking radiation over its lifetime. But the interior geometry, on a timescale much longer than the evaporation time, as seen from outside, undergoes the bounce and expands into a white hole. The matter and information that originally fell in eventually re-emerges from the white hole exit in a highly scrambled form, having spent a very long, proper time inside the bounced geometry. Carlo Rovelli and his collaborators at the Centre de Physique Théorique in Marseille have developed this black hole to white hole transition picture in detail, publishing work on it through the 2000s and into the 2020s. They propose that the bounce happens at the Planck scale of curvature, not of density, and that the proper time for the bounce as seen by an infalling observer is very short, much shorter than the Hawking evaporation time. But the exterior time at which the white hole explosion would be visible is related to the interior time by the extreme time dilation of the black hole geometry, and in these models, it is estimated to be comparable to the Hawking evaporation time, though the precise relationship remains a matter of active debate. This would mean that Hawking evaporation and the white hole bounce are not two separate processes, but two descriptions of the same process. The outside observer sees the black hole slowly losing mass over its Hawking evaporation timescale. The inside observer, if they survive the bounce, experiences the entire interior evolution, including the quantum bounce and the re-expansion, in a finite proper time. The two descriptions are connected by the extreme time dilation between the interior and exterior of the black hole geometry. The information in this picture is not lost. It does not emerge gradually in the Hawking radiation throughout the evaporation. It emerges explosively when the white hole bounces, in a burst of radiation that carries the full information content of everything that ever fell into the black hole. This burst would be the final stage of what, from the outside, looks like the endpoint of Hawking evaporation. Whether this picture is correct is genuinely unknown. It makes specific, though difficult, observational predictions. The white hole bounce would produce a specific spectrum of radiation, different from pure thermal Hawking radiation. And some researchers have speculated that primordial black holes, if they exist, could produce detectable white hole bounces at certain frequencies. But the predictions are at the edge of what any currently planned instrument could detect, and the theoretical underpinning, while mathematically consistent in simplified models, has not been fully extended to realistic, rotating black holes in 4 spacetime dimensions. The string theory picture of the same region gives a different answer. In the string theory framework, the approach to the Planck scale involves the string length scale, roughly the scale at which the description of particles as zero-dimensional points must be replaced by the description of them as extended one-dimensional strings. Near the singularity of a black hole, as curvature grows toward the Planck scale, the string coupling, the strength of interactions between strings, grows large, and the perturbative string theory calculations that work well at low curvature break down. The singularity in this picture is a regime of strong string coupling, whose geometry cannot be described using the perturbative tools that have been the workhorses of string theory. There are, however, non-perturbative techniques. Matrix theory and the various dualities that connect different string theory descriptions in different limits have been used to study strong coupling regimes. In certain highly symmetric cases, the supersymmetric black holes whose fuzzball microstates Mather and collaborators constructed, the singularity is replaced not by a bounce, but by a smooth, complex string geometry that fills the entire black hole interior. The interior of a fuzzball is not empty spacetime. It is a dense tangle of string, a quantum object that fills the volume all the way to the horizon. For a macroscopic observer falling into a fuzzball from the outside, what they encounter at the horizon is not empty space. In the fuzzball description, the surface of the fuzzball, the horizon scale surface, is a quantum string state, not a geometric horizon. The observer encounters the fuzz, not a smooth crossing. Whether this constitutes a firewall in the AMPS sense is debated. Some researchers argue that the fuzzball's surface is microscopically chaotic, but macroscopically feels like a smooth surface, because the energy density of the fuzz at any given point is small. Others argue that the fuzz is genuinely violent, that an infalling observer is disrupted by the quantum string structure at the horizon in a way that is indistinguishable from the firewall prediction. The answer depends on details of the fuzzball construction that have not been fully worked out for macroscopic, non-supersymmetric black holes. This is the central limitation of the fuzzball program. It is well developed for special, ideal cases and extrapolated from those cases to realistic black holes by general arguments that, while compelling, fall short of mathematical proof. Some researchers argue that the extrapolation is justified and that all black holes are fuzzballs. Others argue that the special properties of supersymmetric black holes make them poor guides to the astrophysically relevant case. There is a third string-theoretic approach to the singularity that does not rely on fuzzball technology: the study of space-like singularities using time-dependent string backgrounds. Several groups have studied the behavior of strings propagating in cosmological backgrounds that develop singularities, Big Bang type and Big Crunch type singularities, and have found in some cases that the string interactions become finite even as the classical geometry diverges. The singularity is not resolved into a smooth geometry, as in the loop quantum bounce, but the physical observables, the scattering amplitudes, the string production rates, remain finite. The singularity is, in some sense, penetrable. Strings pass through it, scattered and scrambled, but their information is preserved. If this picture extends to black hole singularities, it would suggest that the singularity is a real but finite event, a place where the geometry becomes singular, but where the quantum dynamics remain well defined and information is preserved, scrambled but intact, with the strings emerging from the singularity into whatever lies on the other side. What lies on the other side is, in these string-theoretic models, typically another spacetime region, either a continuation of the original spacetime with a different geometry, or a connection to a baby universe, or simply the endpoint of the string trajectories without further continuation. The details depend heavily on the specific model and the specific kind of singularity, and general conclusions from special models to realistic black holes remain uncertain. Here is where we must be completely honest about the state of the field. We do not know what happens at the singularity of a real black hole. Every proposal, loop quantum bounce, fuzzball, string resolution, holographic reconstruction, firewall, is a serious, mathematically grounded attempt to answer the question. None of it, them, is confirmed. None of them has produced predictions that have been tested experimentally. The theoretical arguments for each of them are compelling within their own frameworks, and uncertain when those frameworks are pushed beyond their established domains of validity. This is not a failure of the field. It is the expected situation for a problem that requires a complete theory of quantum gravity, which we do not yet have. The black hole interior is the hardest test case in fundamental physics, because it is the place where the two pillars of modern physics, general relativity and quantum mechanics, most directly and irreconcilably conflict, and where the conflict plays out in a region that is, by the causal structure of spacetime, sealed off from direct observation. What we can say is this: the interior of a black hole, as described by any consistent quantum theory of gravity, is not the simple, smooth spacetime of general relativity all the way to a singular center. Something happens at or before the singularity that modifies the classical picture. Something replaces the endpoint of geodesics. Whether that something is a bounce, a fuzz, a stringy resolution, or a holographic reconstruction that changes the very meaning of the interior. The classical picture is not the final answer. And there is something more, something that the various proposals share, despite their differences, that points toward a truth deeper than any specific model. Every proposal that takes both quantum mechanics and gravity seriously, that refuses to simply discard either general relativity's prediction of smooth spacetime near the horizon, or quantum mechanics' insistence on unitarity and information preservation, ends up suggesting that the interior of a black hole and its exterior are not the independent, causally separate regions that classical spacetime description implies. They are connected. The nature of the connection varies by proposal. Entanglement wedges, wormholes, fuzzball surface encoding, island regions. But the connection is always there. This shared feature points towards something profound about the relationship between spacetime and quantum information. The interior of a black hole is not a sealed-off region from which nothing escapes, and in which nothing can be known by the outside. It is a region whose information content is encoded in the exterior through quantum entanglement in a way that classical spacetime geometry does not reveal. The event horizon is a causal barrier to classical information, but not a barrier to quantum correlations. And it is those quantum correlations that carry the information content of the interior out into the Hawking radiation over the evaporation lifetime of the black hole. This is the deepest coherent picture that current physics can offer of what the interior of a black hole contains. It doesn't matter. Not a point of infinite density, not simply a smooth region terminating in mathematical nonsense. But information, encoded in quantum states, distributed through entanglement, preserved by unitarity, and ultimately over timescales that dwarf the age of the universe, returned to the outside world in a form so scrambled that reconstructing the original input would require a computational task of such astronomical difficulty that it would be practically impossible. But that is, in principle, possible. The black hole does not destroy information. It hides it, transforms it, delays it by cosmological timescales, and scrambles it beyond any practical retrieval. But it does not destroy it. This is the current consensus of the most developed theoretical thinking on the subject, held by most, though not all, researchers. It is not a proven fact. It is the conclusion that follows from taking quantum mechanics and holography seriously, from the ADS/CFT correspondence and its implications, from the island formula and the page curve derivation, from the general principle that unitarity must hold in any consistent quantum theory of gravity. But it raises a question that cuts straight to the heart of what a black hole interior is. If the information is encoded in the Hawking radiation, if the interior degrees of freedom are, after the page time, accessible from the outside through quantum entanglement, then what is the interior? Is there a meaningful sense in which the interior of a black hole is a real, physical place? Or is it a derived description, a reconstruction, an emergent picture that dissolves at the quantum level into something that has no geometric description at all? This is where we must go next, into the territory where the concept of space-time itself is under assault, where the most radical proposals suggest that the interior of a black hole is not a place at all, in any fundamental sense, but a pattern of quantum information that we are describing, approximately and incompletely, in the language of geometry. Take a moment to look back at the path we have traveled. We began with darkness, the unremarkable darkness at the center of a black hole, which turns out to be the most consequential darkness in physics. We crossed the event horizon and found that nothing marked the crossing except the inward direction of all futures. We explored the Schwarzschild interior and found that the singularity is in time, not in space. We descended through the Kerr geometry and found the inner Cauchy horizon unstable to perturbations, collapsing into mass inflation. We met Hawking's 1974 result and the information paradox it created. We followed the firewall paradox to the three-way conflict it exposed. We traced the holographic principle and the island formula. We examined the specific quantum gravity proposals: loop quantum bounce, fuzzball, string resolution, and found that each dissolves the simple interior picture into something stranger. And now we arrive at the deepest question of all. The question is not just what is inside a black hole. The question is whether space-time itself, the fabric in which black holes are embedded, the geometry that general relativity describes so precisely, is fundamental or emergent. Whether the smooth, continuous geometry of space-time that we experience and that our instruments confirm is a fundamental feature of reality, or whether it is an effective description, an approximation valid at the scales we probe, emerging from something more fundamental at the quantum level, in the same way that temperature and pressure emerge from the statistical mechanics of atoms. The evidence from black hole physics points strongly in one direction. The Bekenstein-Hawking entropy scales with area, not volume, which is what holography predicts and what emergent space-time theories expect. The island formula shows that geometric regions inside the black hole are encoded in quantum information outside the black hole, which makes sense only if the geometry is a derived description, not a primary one. The ER equals EPR proposal connects entanglement with wormhole geometry, suggesting that space-time geometry is, at least in part, a way of visualizing quantum entanglement structure. In 2013, Mark van Ramsdonk at the University of British Columbia published a prescient paper arguing that entanglement is what holds space-time together. In the language of ADS/CFT, he showed that when the entanglement between two halves of a boundary quantum system is reduced, the corresponding bulk space-time connectivity decreases. The two regions of space-time become less connected, eventually separating entirely if the entanglement is fully severed. Space-time connectivity in this picture is entanglement. The geometry of the interior is the geometry of quantum information. The Einstein field equations, the equations that describe how matter curves space-time, are, in this view, the thermodynamics of entanglement, just as the laws of thermodynamics are the statistical mechanics of atoms. This is an extraordinary idea. It means that the question of what is inside a black hole is not merely a question about an exotic astrophysical object. It is a question about the nature of space itself. What is the interior of a black hole? It is a region of space-time whose geometric existence is conditional on the quantum entanglement that structures it. As the black hole evaporates, the entanglement between the interior and the exterior radiation changes. After the page time, the interior becomes encoded in the radiation, and in the language of Van Ramsdonk's picture, this means the geometric connectivity between the interior and the exterior is established through quantum entanglement. The firewall in this picture would represent a breakdown of entanglement between the interior and the infalling observer, a severing of the quantum thread that holds the smooth interior geometry in place. If you cut the entanglement, the geometry dissolves. The smooth space-time interior ceases to exist as a geometric space because the entanglement that would sustain it has been broken. What the infalling observer encounters is not a smooth crossing into a recognizable interior, but the collapse of the geometric description, and, in the extreme version, a wall of high-energy quanta, the firewall itself. The smooth interior of general relativity in this deep reading is not a discovery about what the interior contains. It is a consequence of entanglement being intact. Destroy the entanglement, and the interior geometry is destroyed with it. This picture, where space-time geometry is entanglement made geometric, is not yet a complete theory. It is a set of insights deriving from multiple directions in the physics literature that converge on a common conclusion without yet crystallizing into a single, mathematically complete framework. But the convergence itself is significant. When ideas from string theory, from loop quantum gravity, from holographic entanglement, from quantum information theory, and from the study of black hole evaporation all point in the same direction, that direction deserves to be taken seriously. The direction they all point in is this: space-time geometry is not fundamental. It is emergent. It emerges from quantum information, from the entanglement structure of quantum states, from the network of quantum correlations that constitutes the true fundamental description of the universe. General relativity, the most precise theory of gravity we have, is not a fundamental theory. It is an effective theory, valid in the classical limit, an extraordinarily accurate approximation at the scales we probe, but ultimately a description of the macroscopic behavior of something more fundamental. What that something more fundamental is precisely we do not know. String theory offers one candidate. Loop quantum gravity offers another. Tensor network models of holography, causal set theory, twistor theory. The field is populated by serious attempts to identify the fundamental degrees of freedom from which space-time emerges. None of them is complete. None of them has produced a prediction that has been experimentally confirmed as evidence of the underlying discrete or quantum structure of space-time. But the black hole, and specifically the black hole interior, is the place where this deeper structure is most urgently needed. The smooth classical interior of general relativity terminates in a singularity, and singularities in physics are not answers. They are questions. They are the places where a theory declares its own incompleteness, where the equations flag their failure, where a more complete description is not optional but mandatory. The black hole singularity is physics at its most urgent. It is the point where the two greatest theories of the 20th century reach their limits simultaneously. It is the place where, if we could somehow see, we would see the fundamental structure of reality laid bare. The quantum nature of space-time, the discrete geometry that underlies the smooth fabric we experience, the origin of the holographic encoding that connects interior to exterior. We cannot see it. Not yet, perhaps not ever in any direct sense. The event horizon seals it from our instruments as certainly as a physical wall. The information paradox, even if resolved, does not give us a window into the interior. The Hawking radiation, even if someday measured with precision for a small black hole, would tell us about the evaporation process, but not about the specific geometry of the interior at any given moment. But we can reason about it. We can constrain it with the principles of physics. We can demand that any consistent description of the interior obey quantum mechanics and general relativity, wherever both apply, resolve their conflict where they disagree, and produce predictions that are mathematically coherent. And this reasoning, pursued with sufficient rigor, has produced one of the most extraordinary transformations in the history of physics. A transformation that goes far beyond black holes, that reaches into cosmology, into the foundations of quantum mechanics, into the structure of space-time at the deepest level. The black hole is not just an extreme astrophysical object. It is a laboratory for quantum gravity, a proving ground for the deepest ideas in fundamental physics, a mirror in which the nature of space-time itself is reflected. Distorted, stranger than we expected, but clearer in its way than anything we could have seen by looking at ordinary matter in ordinary conditions. This is the deepest layer that current physics can describe. Beyond it lies the genuinely unknown, not the unknown of insufficient data or inadequate instruments, but the unknown of absent theory, of questions that our current conceptual framework is not yet equipped to answer. Now we turn to those questions directly. Not to answer them, they cannot be answered yet, but to state them precisely, to understand what kind of questions they are, and to feel the full weight of what it means to stand at the edge of human knowledge and look into a darkness that may never fully yield. What happens at the Planck scale, inside a black hole, in the final microseconds before the infalling observer's proper time runs out? Does quantum geometry bounce, as loop quantum gravity predicts? Does it dissolve into a fuzz of string, as the fuzzball picture suggests? Does it terminate cleanly in a singular boundary, beyond which there is simply no further space-time, as the most literal reading of the Penrose singularity theorem implies? Does it transition into a different space-time region, a white hole, or a baby universe? Or does the very concept of a location, a here, a now, a place where things happen, break down at the Planck scale, leaving not a different geometry but the absence of geometry entirely? We cannot know, not yet, perhaps not ever, given the causal ceiling of the interior. But we can know something. We can know that the question matters profoundly, that the answer, whatever it is, will reshape our understanding of the nature of space and time at the most fundamental level. We can know that the physics community has not stopped asking, that the arguments continue with extraordinary creativity and rigor, that each year brings new mathematical tools and new insights into the constraints that any answer must satisfy. And we can know that the darkness at the center of a black hole, while it yields no photons, no signals, no direct evidence of what lies within, is not empty of meaning. It is the most informationally dense darkness that physics knows, a region in which the information content of an entire collapsed star is encoded, preserved, slowly leaking out through quantum correlations over timescales that dwarf the age of the universe, until finally, in a cold and ancient future, the last Hawking quantum leaves, and the black hole is gone. Gone, but not forgotten. Every bit of information that ever fell in, every quantum state of every particle that ever crossed the horizon, is encoded in the correlations among those outgoing quanta, scrambled to the point of practical irrecoverability, but preserved in principle, intact, waiting for an observer with the computational resources to reconstruct the original state from the final radiation. The darkness gives everything back, eventually. It just takes longer than any human civilization is likely to last. Stand on a hilltop, far from any light pollution, on a clear night when the air is cold and still. Look up. Every object you can see with your naked eye, every star, every smudge of the Milky Way, the faint ellipse of the Andromeda galaxy, if your eyes are sharp enough, is part of the observable universe, the portion of the cosmos from which light has had time to reach us in the 13.8 billion years since the Big Bang. Beyond that boundary, there is more universe, perhaps infinite in extent, from which light has not yet arrived. You are surrounded in every direction by information you cannot access. This is a familiar kind of limitation. We are accustomed to the idea that some things are too far away, too faint, too old for our instruments to reach. What the black hole teaches us is that there is a different kind of inaccessibility, one that is not a matter of distance or sensitivity or time, but of causal structure. The interior of a black hole is not merely far away. it is in a region of space-time that the laws of physics themselves forbid from communicating with the exterior. The darkness inside a black hole is not the darkness of distance. It is the darkness of a one-way door built into the geometry of the universe. And yet, we have been inside. Not physically. No human instrument has crossed a horizon and returned to tell us what it found. But intellectually, we have descended layer by layer through the architecture of what must be there, guided by the most rigorous reasoning in all of science. We have followed the mathematics where it led, even when it led to conclusions that overturned everything we thought we knew about space, time, information, and the nature of reality itself. Now, before we arrive at the final questions, before we stand at the absolute edge of what can be known, this is the right moment to slow down, to breathe, to let what we have already learned settle into the body rather than the mind. Here is what we actually know. Black holes exist. They are not theoretical constructs or mathematical curiosities. They are objects in the universe, formed from collapsed stars and from processes in the early universe. And they sit at the centers of virtually every large galaxy we have observed. Sagittarius A star, at the center of our own Milky Way, has a mass of approximately 4 million solar masses. Its event horizon is a sphere roughly 12 million kilometers across, located 27,000 light-years away in the direction of the constellation Sagittarius. We have photographed its shadow. We have measured the polarization of light spiraling around it. We have watched stars orbiting its enormous gravity in tight ellipses that trace out with perfect fidelity the predictions of general relativity. The black hole at the center of M87, some 55 million light-years away in the Virgo cluster, has a mass of approximately 6.5 billion solar masses. Its event horizon is so large that the entire solar system would fit inside it several times over. Its shadow was the first black hole shadow ever photographed in 2019 by the same global telescope network that later imaged Sagittarius A star. The light ring around its shadow, produced by photons completing nearly full orbits in the extreme curvature before escaping, matches the predictions of the Kerr metric with extraordinary precision. Gravitational waves from colliding black holes have been detected at the LIGO observatories, the Laser Interferometer Gravitational Wave Observatory, with facilities in Livingston, Louisiana, and Hanford, Washington, and at the Virgo Observatory in Cassina, Italy, since the first confirmed detection in September 2015. The waveforms of these mergers match the predictions of numerical general relativity simulations to a precision that would have seemed unimaginable decades ago. We hear the collisions of black holes across hundreds of millions of light-years of space, encoded in the stretching and compressing of space-time itself, measured by instruments sensitive enough to detect a displacement less than 1/10,000th the diameter of a proton. We know black holes are real, rotating, merging objects that obey general relativity with exquisite fidelity, everywhere outside the event horizon. We know that the event horizon is a causal boundary, not a physical wall. We know that the ergosphere exists around a spinning black hole, draining rotational energy through the Penrose process. We know that the Schwarzschild radius determines the horizon scale. We know that the Penrose singularity theorem of 1965 guarantees that something equivalent to a singularity must exist inside every black hole, under the assumptions of general relativity with reasonable energy conditions. We know that the singularity in the Schwarzschild case is space-like, a surface in the future, not a point in space. We know that black holes have a temperature derived by Hawking in 1974, and that this temperature implies they are quantum objects with thermodynamic properties. We know that the entropy of a black hole is proportional to the area of its horizon, as Bekenstein established in 1973, and that this area scaling is the first clear signal that the interior information content is encoded on the surface, the holographic principle. We know that the information paradox is real, that it exposes a genuine conflict between quantum mechanics and general relativity that is not resolved by any currently complete theory. We know that the firewall argument of Almheiri, Marolf, Polchinski and Seeley in 2012 sharpened this conflict to a crisis, a three-way incompatibility between unitarity, quantum field theory in curved spacetime, and Einstein's equivalence principle. We know that the island formula and the derivation of the Page curve in 2019 by Engelhardt and Almheiri represent the most significant recent progress toward resolution, showing that a unitary Page curve can be derived from semi-classical tools augmented by holographic insights. We know that the interior of a black hole, whatever it contains, must be consistent with these constraints. It must preserve information. It must produce a Page curve. It must, in some description, be encodable in the quantum state of the exterior radiation. And it must, somehow, resolve the singularity that general relativity demands. We do not know the mechanism. We do not know whether the correct resolution involves a quantum bounce, a fuzzball, a string-theoretic singularity resolution, a firewall, a holographic reconstruction without a classical interior, or something we have not yet imagined. We do not know which of our current theoretical frameworks is closest to the correct quantum theory of gravity. We do not know whether the smooth interior of general relativity is a good approximation throughout most of the black hole's lifetime, degrading only near the singularity, or whether it breaks down at the horizon itself, as the fuzzball and firewall proposals in their various forms suggest. We cannot know, with any currently existing tool, by any measurement that any currently conceivable instrument could perform. This is not a temporary gap in knowledge of the kind that better telescopes or particle accelerators might fill. It is a fundamental epistemological limit written into the causal structure of spacetime. The interior of a black hole is, by definition, the region from which no signal can escape. Whatever is discovered there by any physical process inside the horizon stays inside the horizon. The only window onto the interior is indirect. The properties of the Hawking radiation, the shadow shape, the gravitational wave ring down after mergers, and these indirect windows carry compressed, scrambled, delocalized information about the interior that would require computational resources of astronomical scale to decode. There is a word in physics for the limit where knowledge simply ends, not because we lack instruments, but because the structure of reality prohibits the information from reaching us. The word is epistemic horizon. The event horizon of a black hole is, in the most literal possible sense, an epistemic horizon, a boundary beyond which knowledge is causally prohibited. And here is what is extraordinary about that. We have thought with great care and rigor about what lies beyond it anyway. Not by peeking through, that is impossible, but by following the logic of physics to its conclusions, by demanding consistency of every proposed description, by letting the mathematics lead us into territory that no physical observer can confirm. The history of physics is full of cases where this kind of reasoning, pursued far enough, revealed truths that later observation confirmed. The existence of Neptune predicted from orbital anomalies before it was seen. The existence of the Higgs boson predicted from the structure of the Standard Model 40 years before its detection. The existence of gravitational waves predicted from general relativity a century before LIGO heard them. The interior of a black hole may be different. The causal barrier of the event horizon may mean that direct confirmation of any prediction about the interior is permanently beyond reach. But the history of indirect knowledge in physics, knowledge derived from consistency requirements, from theoretical constraints, from the demand that the laws governing what we can observe must be consistent with what we cannot, gives some grounds for confidence that the reasoning is not wasted. Something replaces the singularity. Information is preserved. The interior is connected to the exterior through quantum entanglement in ways that transcend the classical causal structure. The geometry of space-time inside a black hole is, in some deep sense, a product of quantum information rather than a primary feature of reality. These conclusions are not certain. They are, in the current state of the field, the most carefully reasoned and broadly consistent answers to the hardest question in fundamental physics. And they point towards something that reaches far beyond black holes. If space-time geometry is emergent from quantum information, if the interior of a black hole is a pattern of entanglement made geometric, then this is not just a fact about extreme astrophysical objects. It is a fact about space-time everywhere. The smooth, continuous geometry of the world around you, the geometry that allows you to measure distances and durations, that governs the motion of every object from a falling apple to an orbiting galaxy, may itself be an emergent description of something more fundamental. The fabric of space-time may be woven from quantum information. The universe may be, at its deepest level, not a collection of objects embedded in a geometric space, but a vast quantum system whose entanglement structure we perceive as geometry. This idea, sometimes called the emergence of space-time from entanglement, or holographic space-time, or the quantum origin of geometry, is not an established fact. It is the frontier of theoretical physics, the edge of what can currently be calculated and checked. But it is the direction that the most serious thinking about black hole interiors consistently leads, and the convergence of multiple independent lines of argument in this direction is itself significant. It means that the black hole, far from being a dead end of physics, a place where theory breaks down and falls silent, is a gateway. It is the place where the limitations of our current description are most clearly exposed, where the inadequacy of treating space-time as fundamental is most sharply demonstrated, where the outline of a deeper theory is most legible. The black hole is not where physics ends. It is where physics begins again, at a deeper level. Sit with this for a moment. Picture yourself back in that clear night sky, looking up at the stars. Each point of light is a sun. Many of them have planets. Some of those planets have conditions that might permit complexity. And somewhere in the direction of the galactic center, 27,000 light-years away, there is a 4 million solar mass black hole, quietly bending space-time, slowly accumulating the stray matter that drifts across its horizon, warming the surrounding gas with the friction of its accretion disk, marking the center of the galaxy with a shadow in radio light. That shadow is the outline of the event horizon. It is the boundary of the known. Everything inside it, the geometry of the interior, the fate of the infalling matter, the resolution of the singularity, the mechanism by which information returns to the universe, is beyond that boundary, sealed by the laws of causality, accessible only through the indirect windows of quantum mechanics and theoretical consistency. And beyond the shadow in the darkness, the questions continue. What does space-time look like at the Planck scale? Is it discrete? Is it a network, a foam, a web of quantum relationships with no continuum limit? Is there a sense in which the word space-time even applies at that scale? or does the concept dissolve entirely, leaving something for which we do not yet have a name? What is the quantum state of the black hole interior? Is it a specific, well-defined quantum state, as the unitarity of evaporation requires? Can it be described geometrically, or is the geometric description an approximation that fails precisely where we most need it? Near the singularity, near the end of the evaporation, near the Planck scale. Is the firewall real? Does an infalling observer encounter something violent at the horizon of an old black hole, or do they pass through smoothly into a classical interior? If the firewall is real, how does physics produce it from the smooth-looking exterior of a black hole? If it is not real, how does information escape without a firewall, and what is the specific mechanism? What is on the other side of the singularity? Is there another side? Does the concept of another side make sense in a theory where geometry is emergent, and the singularity is a breakdown of the geometric description? And beneath all of these specific questions, the deepest one: what is the correct theory of quantum gravity? What is the fundamental description of the universe from which both general relativity and quantum mechanics emerge as limiting cases, each valid in its own domain, each breaking down precisely when the other is needed? We cannot answer these questions today. Some of the physicists who will answer them have not yet been born. Some of the answers may require conceptual breakthroughs of the order of Newton's mechanics, Maxwell's electromagnetism, Einstein's relativity, Heisenberg's quantum mechanics, transformations in the framework of physics so deep that they are barely imaginable from within our current framework. This is what it means to be at the frontier. Not to have answers, but to understand with precision and depth exactly what the questions are and why they matter. To have traced the logic far enough to know where the logic runs out. To stand, as physicists and cosmologists, and anyone who has followed this descent, stand at the edge of the unknown, looking into a darkness that is not empty, but dense with implication. The darkness inside a black hole is the most consequential darkness in science. It is the darkness where quantum mechanics and general relativity collide. It is the darkness where information goes when it can go nowhere else. It is the darkness where the geometry of space-time may dissolve into something more fundamental. It is the darkness that tells us, more clearly than anything else in the observable universe, that our current understanding is incomplete, that the map we have drawn of reality, precise and beautiful and extraordinarily well-tested, does not extend to every corner of the territory. The darkness is an invitation. Every generation of physicists that has stood at this frontier has found, eventually, that the darkness gave way. Newton's mechanics gave way to electromagnetism. Classical physics gave way to quantum mechanics and relativity. Each giving way produced not a destruction of what came before, but an enlargement, a richer framework in which the old framework survived as a limiting case, valid in its domain, superseded in the deeper territory beyond. The giving way that waits inside the black hole will be the largest yet. The framework that replaces our current incomplete understanding of quantum gravity will not merely resolve the information paradox or describe the singularity. It will change what we mean by space. It will change what we mean by time. It will change the relationship between observer and observed in ways that may make even quantum mechanics look like a preliminary sketch. This is not speculation. It is the logical implication of what we already know. The inconsistency between quantum mechanics and general relativity is not a small discrepancy to be patched. It is a fundamental incompatibility that runs through the foundations of both theories. Resolving it requires a revision at the foundation. And revisions at the foundation change everything. The black hole sits at the center of this coming revolution, not as a passive object of study, but as the sharpest test case, the most demanding proving ground, the place where any candidate theory of quantum gravity must pass its hardest examination. Whatever the correct theory of quantum gravity turns out to be, it must describe what happens inside a black hole. It must resolve the singularity, preserve information, produce the page curve, satisfy the constraints of holography, and reduce to general relativity in the classical limit and to quantum field theory in the flat space-time limit. Those are demanding constraints. They narrow the space of possible theories enormously. They may, in the end, point to a unique answer, a single, forced conclusion that the logic of physics requires regardless of which approach we start from. Or they may reveal that the question itself needs to be reformulated, that asking what is inside a black hole presupposes a concept of the inside that is not well defined at the level of quantum gravity, and that the correct answer is not a description of the interior, but a replacement of the question. Both possibilities are live. Both are taken seriously by serious researchers. Both lead in their different ways to the same conclusion, that the interior of a black hole is not the end of the story, but the beginning of the next chapter. There is a moment in the study of any deep subject when the accumulation of complexity gives way to something quieter, when the cascade of ideas, each one building on the last, each one stranger and more demanding than what came before, finally settles into a kind of stillness. Not the stillness of resolution, not the peace of answered questions, but the particular calm that comes from having looked at something honestly and completely, from having followed the argument wherever it led without flinching, and from having arrived at last at the place where the argument itself acknowledges its own limits. We are at that place now. We descended into a black hole together, layer by layer, and here is what we found at each level of the descent. At the outermost layer, we found the event horizon. Not a wall, not a surface, not a physical object of any kind, but a causal boundary written into the geometry of space-time. A location defined entirely by what cannot happen there. Light cannot leave, signals cannot escape. And yet, crossing it feels like nothing for an observer in falling into a sufficiently large black hole. The drama that popular imagination associates with the event horizon, the crushing force, the dramatic transition, is not there. What is there is subtler and stranger. The future has changed. Every path through space-time, every trajectory forward in time now points inward. The event horizon is the moment when the center becomes the future. At the next layer, inside the Schwarzschild geometry, we found the exchange of time and space. The singularity is not ahead of you in space. It is ahead of you in time. You cannot fly around it or avoid it by maneuvering. You are being carried toward it by the flow of time itself, just as you are being carried toward tomorrow. This transformation, the space-like singularity as the future interior, is one of the most profound and least discussed features of general relativity's description of black holes. It changes everything about how we should think of what the interior contains. Descending further into the Kerr geometry of a real rotating black hole, we found the ergosphere, the frame dragging of space-time itself, the Penrose process by which energy can be extracted from the rotation of the black hole. We found the inner Cauchy horizon, which the ideal Kerr solution permits, but which perturbations, the realistic imperfections of any real black hole formed from real matter, render unstable, collapsing into a mass inflation singularity that is more honest, perhaps, about what a realistic black hole interior actually contains. Below that, we met Roger Penrose's 1965 theorem, a proof, not a conjecture, a mathematical argument that, Given general relativity and reasonable assumptions about matter, every black hole must contain a singularity, a place where geodesics simply stop, where the manifold ends, where the equations produce no further future. A theorem that guarantees the presence of something without specifying what that something is. A theorem that demands we go beyond general relativity to understand what it means. And then the quantum arrived, in the form of Hawking's 1974 calculation. The event horizon has a temperature. Black holes radiate. They lose mass. They evaporate. And in that evaporation, the information paradox emerges. The conflict between quantum mechanics' insistence that information is never destroyed and Hawking radiation's apparently featureless thermal nature, which carries no information about what fell in. Don Page's 1993 insight about the curve that unitary evaporation must trace. The firewall paradox of Almheri, Marolf, Polchinski, and Sully in 2012, sharpening the conflict into a three-way incompatibility between unitarity, quantum field theory, and the equivalence principle. The Island formula and Engelhart's work in 2019, showing that the Page curve can be derived within a semi-classical framework, augmented by holographic insights. Throughout all of it, a single thread pulled everything together: the holographic principle. The insight that the information content of a black hole scales with the area of its horizon, not its volume. That the interior is somehow encoded in the exterior. That the entanglement between the Hawking radiation and the black hole interior carries over the evaporation lifetime all the information that ever fell in. That geometry is not primary but emergent, woven from the entanglement structure of quantum states, following the logic of van Raamsdonk's 2013 insight that space-time connectivity is entanglement made geometric. And at the deepest level, where the proposals diverge and the certainty dissolves, we found the honest answer. We do not know. The loop quantum bounce, the fuzzball, the string theoretic resolution, the holographic interior, each is a serious, constrained, mathematically grounded proposal. None is confirmed. The question of what actually happens at the Planck scale inside a black hole is, in the most rigorous sense, an open question. The theory that would answer it does not yet fully exist. This honest uncertainty is not a failure. It is the natural state of physics at its frontier. Every generation inherits the unresolved questions of the previous one and passes on a new set of unresolved questions to the next. The questions that wait inside a black hole are not the questions of a field that has stalled. They are the questions of a field that has pushed so hard against the boundary of the known that the boundary itself has become the subject. That the shape of what we cannot know has become something we can describe and measure and argue about with extraordinary precision. There is a historical parallel worth drawing here, and it is one that deserves careful attention. In the late 19th century, physics appeared to many of its practitioners to be nearly complete. The laws of mechanics, electromagnetism, thermodynamics, and optics had been established. The major experimental phenomena were understood. There were a few outstanding puzzles: the blackbody radiation spectrum, the photoelectric effect, the failure to detect the luminiferous ether through which light was supposed to travel. But these seemed like minor loose ends, details to be filled in rather than signs of fundamental incompleteness. Then came the decade between 1900 and 1910. Planck introduced the quantum to explain the blackbody spectrum in 1900. Einstein explained the photoelectric effect with photons in 1905, and in the same year published Special Relativity, which dissolved the ether and transformed the concept of spacetime. Rutherford discovered the atomic nucleus in 1909. Within a decade, the near-complete physics of the late 19th century had been revealed as a classical approximation, valid at human scales, with an entirely different and far stranger reality underlying it at small scales and high velocities. The outstanding puzzles were not minor details. They were symptoms of the deepest incompleteness in the framework. The information paradox, the singularity problem, the conflict between quantum mechanics and general relativity. These are the outstanding puzzles of today. They have resisted resolution for half a century. They cannot be resolved within the existing framework. They are not minor details, they are symptoms. What lies beyond them? The quantum theory of gravity that will resolve the singularity, preserve information, explain the holographic encoding of the interior in the exterior, and reduce to both general relativity and quantum mechanics in their respective domains, will transform our understanding of reality as profoundly as the transition from classical to quantum physics transformed the understanding of the early 20th century, perhaps more profoundly. Because what the black hole physics tells us is that the transformation will not be merely about adding a new layer of description at a smaller scale, the way quantum mechanics added to classical mechanics. It will be about the nature of space and time themselves. It will dissolve the continuum of space-time and replace it with something discrete, or informational, or holographic, or some combination of all three that we cannot fully anticipate from within the current framework. When that transformation comes, and it will come, because the pressure of the questions is too great, and the tools of physics too powerful for the questions to remain unanswered forever, the black hole will be seen as the place where it had to come, the place where the existing framework was most visibly and most urgently inadequate, the place where the questions were sharpest and the stakes highest. The darkness at the center of a black hole is not the darkness of ignorance. It is the darkness of a question that is perfectly formulated but not yet answered. It is the darkness of a problem that physics has correctly identified and not yet solved. It is the most productive darkness in science, the kind that generates, in the researchers who sit with it long enough, the determination to find the deeper framework that makes it legible. And when you step back from all the technical details, the Cauchy horizons, and the island formulas, and the fuzzball microstates, and the page curves, and the spin networks, and the entanglement wedges, when you let the technical landscape recede and hold only the essential shape of what we have explored, what remains is something that is both scientifically precise and quietly beautiful. A black hole is a region of space-time that has folded in on itself so completely that time itself points inward. Inside it, the ordinary architecture of reality, the separation of time from space, the ability to move in any direction, the causal connection between here and there, has been replaced by something simpler and more absolute, an inward future and a singular end. Everything that falls in becomes part of that interior, encoded in the quantum correlations of the Hawking radiation that slowly leaks away over timescales so vast they make the current age of the universe look like a brief morning. And eventually, after all the radiation has departed and the black hole has evaporated entirely, every bit of information that ever fell in is present, in principle, in the remaining radiation, scrambled beyond any practical recovery, but intact, preserved, unhidden by the deepest laws of quantum mechanics. The universe does not forget. It only delays. That is what is really inside a black hole, not a point of infinite density. That is a mathematical symptom of incomplete physics, not a sealed-off void that swallows everything without remainder. That is a classical misreading of quantum reality. What is inside a black hole is a compressed, encoded, temporally sealed library of everything that ever fell through the event horizon, held in quantum correlations that span the causal boundary, leaking out one entangled photon at a time over eons, until the library has been completely, irreversibly, and unreadably returned to the universe from which it came. The black hole is the universe's deepest archivist, and the darkness at its center is not the darkness of loss. It is the darkness of waiting. We began with a simple observation. The darkness at the center of a black hole is different from any other darkness. Every shadow you have ever seen is simply light blocked. The darkness at the center of a black hole is the place where the geometry of reality breaks, where time ends, where our best equations produce values that are literally undefined. Where the most honest answer physics can offer is that we have reached the boundary of what general relativity can say, and a more complete theory must take over. Now, at the end of this descent, that darkness is the same, still sealed, still inaccessible, still producing no signal that any instrument can intercept. But it is not the same for us. We have traced the shape of what it must contain. We have followed the logic of physics into territory that no spacecraft will ever enter and no signal will ever return from. We have stood, intellectually, at the edge of the singularity and looked at the boundary of the known and understood, with a precision that only the hard discipline of physics can provide, exactly what we do not know and exactly why it matters. If this changed how you think about darkness, about space, about the nature of information and the geometry of time, if the event horizon feels less like a wall and more like a threshold, if the singularity feels less like a place and more like a question, if the silence of the black hole interior sounds less like absence and more like an answer waiting to be found, then the time we spent together descending into one of the universe's most profound mysteries was time genuinely well spent. Thank you for staying. Thank you for holding still in the dark and listening for the physics underneath the darkness. The questions that wait at the center of a black hole are the most important questions in fundamental science, and the fact that they are still open means that the greatest chapter of this story has not yet been written. The darkness is still there, and the work continues.